All right, let's try this again. I already made one of these, but I didn't turn the microphone on, so that's awesome. But now I'm really good at this. So quick equilibrium intro. Sorry, my writing looks like a gorilla, but an intelligent gorilla anyways. With equilibrium, if you guys looked at those notes, now we're dealing with forward and reverse reactions. So instead of just like a forward arrow like we've used previously, we're going to do a forward arrow and a reverse arrow. You can draw them like that. Sometimes I draw them like that to save some time, or you might even see them like just like a double arrow on either end. So that's what we're looking at, forward reaction and a reverse reaction. You need a closed system, so you can't let any reactants or products be escaping, or else we won't be able to set up an equilibrium. So that's important. And then this one is the big one. This is the definition of equilibrium. So the rate of the forward reaction is equal to the rate of the reverse reaction. If those are happening at the same time and at the same rate, we won't actually see any changes, because every time reactants get turned into products, products get turned into reactants, and we don't see any changes in our system. A lot of people think equilibrium is equal amounts of reactants and products, and sometimes that's the case, but not usually. So this is the definition of equilibrium. Rate of the forward reaction equals rate of the reverse reaction. So just as a quick example here, somewhere, I had this one in the notes. This is kind of a cool system. This is hydrogen iodine gas reacting, and they're going on and making hydrogen iodide. So there's the two reactions happening right there. So there's a forward reaction and there's a reverse reaction when the hydrogen iodide splits up and turns back into the elemental gases. This one's cool because iodine gas is nice purple color. So initially in this flask, there's some hydrogen gas and some iodine gas, so really, really purple. As it reacts, hydrogen iodide is not colored. So as the iodine gets used up, our purple color starts to go away. So it gets a little bit lighter here. That'll continue to react. As hydrogen and iodine run into each other, they'll react to make hydrogen iodide. But then as we make more hydrogen iodide, it'll actually turn backwards and start that reverse reaction. So we have kind of both those reactions happening at the same time. And eventually we'll get to a flask that has a really steady purple color. It means nothing's changing anymore. Our forward reaction rate is equal to our reverse reaction rate, and we've hit equilibrium. So that one's kind of neat. Again, if you looked at the notes, there's some different systems that go along with this one. They're just some examples of different systems. So this first system is kind of like what they did up above. They put in some hydrogen gas and some iodine gas with no hydrogen iodide initially, so that really dark purple color. Those reacted back and forth, and then at equilibrium, we ended up with some hydrogen gas, some iodine gas, and some hydrogen iodide gas. System 2 puts in all three of the gases, so a big mixture of them all together. There's a little bit of a change to reach equilibrium, so it looks like the hydrogen iodine decreased a little bit, and the hydrogen iodide increased a little bit, so it kind of shifted towards the product side. But again, we've hit equilibrium with all three gases kind of together. System 3 kind of does the reverse of System 1. It doesn't put any of the reactants in. It only puts in hydrogen iodide, that thing on the product side. But it will break down into hydrogen iodine. And again, we get a mixture of all those gases together. What we'll look at later is with equilibrium constants and things like that. All of these values here, because they're occurring at the same temperature, we actually get the same ratio between reactants and products. Turns out to be about 78% products. So you can see there's mostly products there versus the reactants. There's less of them. So that system's kind of cool. Sometimes you guys will see this. So here's our reaction happening. Forward and reverse reaction. And you can actually write that percentage right over top of the arrow. The other way you might see these presented is as a graph. So this graph shows we put in a little bit of hydrogen gas and iodine gas initially. There's no hydrogen iodide initially. These two decrease as they react to make the hydrogen iodide, and then eventually they all kind of smooth out at a constant amount. Usually we'll use concentration here, and that means we've hit equilibrium. So flat lines on a graph, horizontal lines, means we're at equilibrium. So there you go. Real quick, if you see those percentages, if it's a greater than 50% reaction, we say it favors the products. So it just means that at equilibrium we have more products than reactants, so kind of like this system here. Less than 50% means it hasn't gone a whole lot to the product side, so we say it favors the left-hand side, or what we call the reactants. And then sometimes you'll have equal amounts reactants and products, and that would be like your 50% reaction. 0%, if it doesn't react at all, if it stays just as reactants, then that's just a non-spontaneous reaction. So there you go. Hopefully that helps. Stay tuned. I'll post some more stuff on some K values coming up.